Today, we're diving deep into a whole stack of sources, some cutting-edge research papers, some really broad analyses to pull out the key insights for you. Our mission, really, is to cut through all the complexity, uh, give you a clear shortcut to understanding this new era of quantum tech, what's driving it, and importantly, why it matters to you.
It is a huge shift. And, what's fascinating is the basic quantum laws themselves, they're nearly a century old.
Mhm.
But it's this new, unprecedented ability we have to actually manipulate individual quantum systems like single atoms or electrons, single photons, that really defines this current revolution. It's a move from, let's say, passive understanding to active engineering, a really profound change.
Okay, let's try and unpack that a bit. What exactly is this second quantum revolution? How is it different from, well, the first one?
Yeah, good question. Think of it like this. The first quantum revolution gave us things like transistors, lasers, right?
Mm.
It worked by using the collective quantum behavior of, well, loads of particles together. It was about understanding materials like semiconductors.
No.
This second revolution, though, it's all about control, precision control, isolating and manipulating individual quantum systems one by one, one atom, one photon at a time, and using that control to build completely new kinds of technology.
So the first revolution built the foundation for our digital age, basically. But the second one is more like actively programming the very building blocks of reality itself. That feels like a massive leap.
That's a great way to put it. Exactly. The early 20th century, you had the pioneers Planck, Einstein, Schrödinger, Heisenberg wrestling with these bizarre quantum rules.
Hmm.
And that work led to amazing tech. Semiconductors, MRIs, atomic clocks. Now, we're building directly on that knowledge, but with this incredible new level of fine-tuned control.
And entanglement seems to be at the heart of this. That's the concept Einstein famously called spooky action at a distance, right? What does that actually mean in practice?
Well, it's this incredibly deep connection between two or more quantum particles. They become linked, fundamentally intertwined, no matter how far apart they are. So if you measure something about one particle, you instantly know the corresponding thing about the other one, even if it's light years away. It sounds weird, I know.
It does sound spooky.
It really does. And for decades, honestly, it was mostly a philosophical puzzle, something theorists debated. But then in the 1960s, this brilliant physicist, John Bell, came up with a mathematical way to actually test it, Bell's inequalities.
Ah, okay. So it moved from just theory into something you could actually test in a lab.
Precisely. And that's exactly what Lane Aspect and his team did in the 1980s. Their experiments proved, really conclusively, that entanglement was real. It wasn't just a quirk of the math. That was the turning point. It showed entanglement wasn't some paradox, but a real harnessable feature of the universe. And that realization, that's what really gave birth to the whole field of quantum information science. It shifted the question from, what does quantum mechanics tell us, to, okay, what can we make the world do using quantum mechanics?
That's a huge pivot. So we're talking about building machines where the actual operations are engineered quantum mechanics. Wow. And you mentioned this is happening across, what, four main areas? Quantum computing, communication, sensing, and simulation.
That's right, four interconnected pillars.
Let's start with the one most people think of first, quantum computing. How is it so fundamentally different from the computers we all use every day?
Okay, so the core difference lies in the basic unit of information. Classical computers use bits, which are either a 0 or a 1. Simple enough. Quantum computers use qubits. And thanks to a quantum effect called superposition, a qubit can be a 0, a 1, or somehow both 0 and 1 at the same time.
Both at one.
Both at once. And it gets better. When you link qubits together using entanglement, the number of possibilities they can represent grows exponentially. So imagine a classical computer trying out solutions one after another. A quantum computer, because of superposition and entanglement, can explore vast numbers of possibilities simultaneously. We call this quantum parallelism.
So it's not just about being faster, it's a completely different way of tackling problems. That sounds incredibly powerful. How are people actually building these qubits? What are the main approaches?
Yeah, there isn't just one way. There are a few leading contenders right now, and they all have their own strengths and weaknesses. First, you have superconducting circuits. These are like tiny artificial atoms made from superconducting materials, cooled down to incredibly low temperatures, near absolute zero. They're very fast. Operations take nanoseconds. And companies like IBM and Google have made huge progress building chips with hundreds, even over 1,000 qubits now. The main challenge: their quantum states are very fragile. They don't last long before errors creep in. That's called coherence time.
Okay, so speed is good, but stability is tricky. What else?
Then there are trapped ions. Here you take individual atoms, zap them with a laser to knock off an electron so they have a charge, they become ions, and then you trap them using electromagnetic fields. You control them with more lasers. Their big advantage is stability and accuracy. They have incredibly long coherence time seconds, sometimes even minutes, and very high fidelities, meaning fewer errors. Companies like Quantinuum and IonQ are leaders here. The difficulty is often scaling them up, getting lots of them to work together efficiently, especially beyond just a simple line of ions.
Interesting trade-offs. And you mentioned a third.
Yes, neutral atoms. Instead of ions, you use neutral atoms, holding them in place with arrays of tightly focused laser beams called optical tweezers. These systems scale really well. Researchers have demonstrated arrays with hundreds of atoms packed closely together. They also have pretty good coherence times. The catch is sometimes the interactions between qubits can be a bit slower, or the accuracy of operations involving two qubits might be a bit lower than trapped ions, for example. Query computing is a notable player here.
So it really feels like a race, with different teams betting on different horses, trying to balance stability, speed, scale.
Absolutely. And there are other approaches too, like using photons, particles of light, as qubits, which has advantages for communication. It's a really dynamic field.
Okay, so that's the hardware. What about the software? We hear about these potentially world-changing algorithms, like Shor's algorithm breaking encryption or Grover's for searching. Are we running those yet?
Not on a practical scale, no, not yet. We're currently in what people call the NACE-Q era. That stands for a noisy intermediate scale quantum. Our current quantum processors are impressive, definitely intermediate scale, but there's still noisy errors build up quickly and limit the complexity of calculations we can do reliably.
Right, the noise problem again.
Exactly. So right now, the focus is a lot on hybrid quantum classical algorithms. The quantum computer tackles a specific hard part of a problem where it has an edge and then hands results back to a classical computer to finish the job. Algorithms like VQE or QAOA fall into this category, aiming for near-term applications in chemistry or optimization. We're still building towards the truly fault-tolerant machines needed for things like Shor's algorithm.
Got it. So hybrid approaches for now.
Fascinating. Okay, moving from computing to communication.
Yeah.
The second pillar. How does quantum mechanics offer, fundamentally secure communication?
It boils down to a couple of really core quantum principles. First is the no cloning theorem. It basically says you cannot make a perfect copy of an unknown quantum state, just impossible.
Can't copy it. Okay. Second, the act of measuring a quantum state inevitably disturbs it. You can't observe it without changing it, fundamentally. So put those together. If an eavesdropper, let's call her Eve, tries to intercept and copy a quantum message, she can't make a perfect copy. And if she tries to measure it to read it, she will distort it. That disturbance leaves an undeniable trace, alerting the legitimate parties, Alice and Bob, that someone was listening.
Wow. So security isn't just based on making it computationally difficult to crack, like current encryption. It's built into the physics. You literally can't eavesdrop without being detected.
That's the promise, exactly. It's physics-based security. This is the foundation for quantum key distribution, or QKD. It allows Alice and Bob to generate and share a secret encryption key, knowing with certainty, based on the laws of physics, that no one else could possibly have intercepted it without revealing themselves.
And this is actually being used.
Oh yes, there's been incredible progress. QKD systems have demonstrated secure key exchange over hundreds of kilometers of standard optical fiber. And probably the most famous example is China's Misha satellite, which successfully enabled intercontinental quantum-secured video calls between China and Austria. So it's moving beyond the lab.
That's amazing. And the bigger vision is a full quantum internet, sending qubits around the world.
That's the long-term dream, yes.
Yeah.
A network that doesn't just send classical bits, but actual quantum states, qubits. Think about the applications. You could link quantum computers together for distributed quantum computing, creating a machine much more powerful than any single device, or create networks of ultra-precise quantum sensors for astronomy or geology, and enhance security protocols even further.
But didn't you say earlier you can't just amplify quantum signals? How do you send them long distance?
Ah, yes, that's the major hurdle. Signal loss is inevitable over long distances, and you can't use classical amplifiers because measuring and retransmitting destroys the quantum state.
Yeah.
The key enabling technology needed here is the quantum repeater. It's a complex device that uses clever tricks like entanglement swapping and rudimentary quantum error correction to pass the quantum state along segment by segment without ever directly measuring the fragile information it carries. Building reliable quantum repeaters is a huge area of research right now.
Crucial technology then. Okay, let's shift to the third pillar, quantum sensing and metrology. You hinted at this earlier. It almost seems like this sensitivity, the fragility that's a challenge for computing becomes a superpower here.
You've nailed it. That's exactly right. The very fact that quantum systems are so exquisitely sensitive to tiny changes in their environment, magnetic fields, gravity, temperature, time, makes them phenomenal sensors. By harnessing superposition and entanglement, we can push measurement precision far beyond what any classical device can achieve. We're basically turning that bug of environmental sensitivity into a killer feature for measurement.
Can you give some concrete examples? Where is this making a difference already, or where will it soon?
Sure. Well, think about timekeeping. The atomic clocks that underpin things like GPS are already a product of the first quantum revolution, right? But new generations of optical and quantum clocks are pushing accuracy to mind-boggling levels. Then there are quantum magnetometers. Devices like SQUEED or newer atomic magnetometers can detect incredibly faint magnetic fields. This is useful in medicine for mapping brain activity magnetoencephalography, or MEG, or in geology for finding mineral deposits, even for defense applications like detecting submarines or navigating where GPS is denied.
Wow, really diverse applications.
Absolutely. And there's more. Quantum gravimeters and accelerometers use techniques like atom interferometry to measure tiny variations in gravity or acceleration. That's useful for finding underground resources, monitoring volcanoes, or developing ultra-precise inertial navigation systems. Even quantum imaging is emerging, using effects like ghost imaging or squeezed light to see through fog or smoke, or to image delicate biological samples with less damaging light. Honestly, quantum sensing is arguably the most mature of the four pillars commercially. You're probably already benefiting from early forms of it, like those atomic clocks in the GPS system.
It really shows how pervasive this could become. Okay, the final pillar, quantum simulation. This goes back to Richard Feynman's idea from the 80s, right? Using a quantum system to simulate another quantum system.
That's the origin, yeah. Feynman's famous quote, "Nature isn't classical, damn it." He realized that trying to simulate complex quantum systems like molecules or materials on classical computers quickly becomes impossibly hard. The computational cost just explodes. His insight was, why not build a computer that operates on the same quantum principles? Use a controllable quantum system to mimic or simulate another, less accessible one.
Because classical computers just can't keep up with quantum complexity.
Exactly. Simulating even moderately complex molecules requires computational resources far beyond any conceivable classical supercomputer. But a quantum simulator, because it is a quantum system, can naturally handle that complexity. It speaks the same language.
Are there different types of these simulators?
Broadly, yes. There are two main flavors. Analog quantum simulators are special-purpose devices built to mimic the specific interactions, the Hamiltonian, technically, of a particular target system. Think of them like a physical model. They're often easier to build in the near term and less demanding on qubit quality. We're already seeing analog simulators, like some neutral atom platforms, tackle specific scientific problems that are tough for classical machines, achieving what's sometimes called practical quantum advantage.
Okay, like a custom-built quantum model.
Right. And then there are digital quantum simulators. This is essentially running a simulation algorithm on a universal gate-based quantum computer, the kind we talked about earlier. It's more flexible. You can simulate potentially any quantum system if your computer is powerful enough, but it requires that fault-tolerant hardware that we don't quite have yet at scale.
And the potential impact here, especially for industries.
Oh, it's huge. Really huge. Think about material science. Designing new materials from the ground up, maybe room temperature superconductors, much better catalysts for green chemistry, more efficient solar panel materials, improved batteries, or quantum chemistry and drug discovery. Simulating how drug molecules interact with proteins in the body could drastically cut down the time and cost of developing new medicines. Finding new catalysts for industrial processes could make them way more efficient and environmentally friendly.
It sounds like it could revolutionize R&D in multiple fields.
That's the hope. And it's important to remember these four pillars, computing, communication, sensing, simulation, they aren't isolated silos. They're deeply interconnected. Better quantum sensors help us build better qubits for computers. Quantum simulators help design new materials for sensors or communication links. Quantum networks could connect simulators and computers. Progress in one area often fuels progress in others.
That makes sense. It's a whole ecosystem developing. So we've laid out what these amazing potential technologies, but let's dig into the how. How do we actually do all this? The basic physics ideas have been around, but you said the real revolution is in the engineering, right? Controlling things at that tiny scale.
Absolutely. Mastering the single quantum state is job one. And a key enabling technology here has been laser cooling and trapping. Scientists figured out how to use precisely tuned lasers to slow down atoms until they're incredibly cold, billionths of a degree above absolute zero.
Colder than space.
Much, much colder. And then they use other lasers, like optical tweezers or electromagnetic fields, to hold these individual atoms or ions perfectly still in space. This ability to isolate and hold single quantum particles is the essential starting point for many quantum computers and sensors.
Okay, so you trap them. Then how do you control their quantum state?
That's where advanced control technology comes in. For trapped ions or neutral atoms, it's often incredibly precise sequences of laser pulses. For superconducting qubits, it's carefully shaped microwave pulses. We're talking about controlling these states with unbelievable accuracy. There was a record reported, I think from Oxford, achieving control accuracy on a trapped ion qubit with an error rate of something like 1 in almost 7 million. That level of precision is just staggering, and it's built on decades of advances in laser and microwave technology.
Incredible precision. And you mentioned earlier that the quality of the qubits themselves, especially how long they stay, their coherence time, is critical.
It's absolutely crucial. Extending coherence time is a constant battle against environmental noise. And a lot of that comes down to materials science. For instance, in superconducting qubits, researchers found that using tantalum instead of niobium could lead to better surface quality, reducing microwave energy loss and boosting coherence times significantly, past 0.3 milliseconds in some cases. It's about eliminating tiny imperfections, microscopic defects, stray particles, anything that can absorb energy and disturb the qubit.
So it's materials science at an almost atomic level.
It really is. Similarly, for semiconductor qubits made from silicon, scientists use isotopic purification, enriching the silicon in one specific isotope, silicon-28, to remove the magnetic noise from other silicon isotopes that can mess with the qubit's spin state. And all of this relies heavily on borrowing and adapting the incredibly sophisticated precision fabrication techniques developed over decades by the classical semiconductor industry. Things like molecular beam epitaxy, photolithography, allowing us to build structures with near-atomic scale control.
And keeping things stable often means keeping them incredibly cold. You mentioned near absolute zero.
For many leading platforms, yes, especially superconducting qubits and some types of semiconductor qubits. The workhorse technology here is the dilution refrigerator. These use a mixture of helium isotopes to reach temperatures in the millikelvin range, just thousandths of a degree above absolute zero.
That sounds bulky and energy intensive.
Traditionally, yes. But there's a lot of innovation happening to make cryogenics more compact, more power efficient, and better at handling the heat generated by the control wiring and the qubits themselves. A really key area here is developing cryo-CMOS electronics, designing classical control chips using CMOS technology like standard computer chips that can actually operate inside the coldest part of the refrigerator right next to the quantum chip.
Putting the control electronics in the freezer with the qubits.
Exactly. It drastically reduces the number of wires running from room temperature down into the fridge, which cuts down on heat leaking in and sources of noise. It's seen as absolutely essential for scaling up to thousands or millions of qubits.
So it really drives home the point that a working quantum computer isn't purely quantum. It's this intricate hybrid system.
Absolutely. It's a sophisticated marriage of quantum and classical. You need all that high-performance classical hardware waveform generators, creating the precise control pulses, low-noise amplifiers, reading out the faint qubit signals. But maybe the biggest classical challenge, especially looking towards fault-tolerant machines, is the real-time feedback needed for quantum error correction.
Ah, the QEC loop you mentioned earlier.
Right. That whole cycle, measure the error syndrome using ancillary qubits, have a classical computer rapidly decode what kind of error occurred and where, and then send signals back to apply a corrective pulse. All of that has to happen incredibly fast. We're talking within a microsecond or so.
A millionth of a second.
Yes. Before the quantum state decoheres further. That demands extremely fast, low-latency, classical processing tightly integrated with the quantum hardware. So connecting this all together, these enabling technologies really show that this quantum revolution is as much about phenomenal precision engineering as it is about fundamental physics. The bottleneck is rapidly shifting from, can we control one qubit really well, to can we engineer systems to reliably control and interconnect millions of them, along with all the necessary classical support.
That's a monumental engineering challenge, and it leads us right into the core problem that needs solving for scalability, this inherent quantum fragility or decoherence. You mentioned we're in the NAQ era, noisy intermediate scale quantum, because errors just pile up too quickly in current devices, right?
That's the essence of it. Decoherence is the enemy. It's the quantum system losing its quantumness, its superposition and entanglement, because of unavoidable interactions with its surrounding environment. Heat, stray electromagnetic fields, even tiny vibrations can cause errors. In at-ICE-Q devices, these errors accumulate so fast that for complex calculations, the noise quickly overwhelms any potential quantum advantage. The signal gets lost in the noise.
So how do we actually fix the errors, not just mitigate them? You mentioned quantum error correction, QEC, as the long-term solution.
Exactly. For near-term at-ICE-Q computing, people use quantum error mitigation, QEM techniques. This involves clever strategies like running the computation many times, varying the noise levels, and then classically processing the results to extrapolate what the ideal error-free answer would have been. QEM is useful. It helps us get more out of today's noisy machines, but it doesn't fundamentally correct errors as they happen, and its effectiveness generally decreases as computations get larger. It doesn't scale to truly complex problems. The ultimate goal, the holy grail for scalable quantum computing, is quantum error correction, QEC.
Right. And standard ways of correcting errors, like just making copies, don't work in quantum, you said?
Correct. Classical error correction often relies on redundancy, making multiple copies of a bit, and using majority voting. But the no-cloning theorem says you can't copy an unknown qubit, and measuring a qubit to check for errors destroys its superposition. So classical methods are out. This is why Peter Shor's 1995 discovery of QEC was such a massive theoretical breakthrough. He showed it was possible, but required a completely different approach.
How does it work, conceptually?
The core idea is ingenious. Instead of storing your quantum information in a single fragile physical qubit, you encode it redundantly across multiple physical qubits that are all entangled together. This combined entity forms one, much more robust logical qubit. Then you use other helper qubits, called ancillary qubits, to perform collective measurements on parts of the encoded state. These measurements are designed very carefully so they reveal information about whether an error occurred and what type of error, but without revealing or disturbing the actual quantum information stored in the logical qubit.
So you can detect errors without actually looking at the data itself.
Precisely. These measurements give you an error syndrome. A classical computer then takes this syndrome information, runs a decoding algorithm to figure out the most likely error and where it happened, and then sends instructions back to the quantum hardware to apply a corrective operation, like flipping a qubit back if it got flipped.
That sounds incredibly complex. Does it always work?
Well, there's a crucial catch. QEC only provides a net benefit if the error rate of the underlying physical qubits and operations is already below a certain level, known as the fault tolerance threshold. If your physical components are too noisy above the threshold, the process of error correction itself actually introduces more errors than it fixes. So getting physical qubit quality high enough to be below this threshold is a paramount goal for all hardware platforms.
Okay, so you need good physical qubits first. And I imagine encoding one logical qubit using many physical ones means you need a lot of physical qubits.
That's been the major challenge to resource overhead. Historically, the most studied QEC codes, like the surface code, while having relatively good thresholds and only requiring local interactions, which suits some hardware like superconducting chips, demanded a huge number of physical qubits for each logical qubit. We're talking potentially thousands, maybe even millions of physical qubits to get just a few thousand useful logical qubits for a significant computation.
Millions for thousands. That's a huge overhead.
It is. But this is where some really exciting recent developments come in. Researchers are intensely exploring alternative QEC codes that could be much more efficient. A particularly promising family is known as quantum low-density parity check codes, or QLDPC codes. These codes have theoretical properties suggesting they could offer much better scaling, meaning you might need significantly fewer physical qubits per logical qubit, especially for larger computers. And just recently, there was a landmark experimental demonstration and design by teams involving IBM and UC Berkeley using a type of QLDPC code, sometimes called a gross code, where they showed a path to encoding 12 logical qubits using only 288 physical ones. That's roughly a tenfold improvement in overhead compared to what early service code estimates suggested.
A tenfold improvement. That sounds like a potential game changer for making fault-tolerant computers feasible sooner.
It really could be. Lowering the qubit overhead makes the engineering challenge significantly less daunting.
Does the rise of these potentially more efficient codes like QLDPC change the landscape for the different hardware platforms we talked about earlier?
It absolutely could. Many of these advanced QLDPC codes require more complex patterns of connections between the physical qubits, not just nearest neighbor interactions like the surface code often assumes. This might play to the strengths of platforms like trapped ions or neutral atoms, where qubits can potentially be connected over longer distances or reconfigured more flexibly compared to, say, superconducting qubits, which are often fixed on a chip with primarily local connections. So the best hardware platform might not be decided in isolation. It could depend heavily on which platform best supports the most efficient fault-tolerant QEC architecture. The interplay between codes and hardware is critical.
So the race isn't just about building more qubits, but building the right kind of interconnected qubits for error correction.
Exactly. And it loops back to the classical side, too. Remember that fault-tolerant quantum computer is really a hybrid supercomputer. That classical control system performing the QEC decoding and feedback needs to be incredibly powerful and fast. Some estimates suggest that managing error correction for, say, 1 million physical qubits might require processing data at rates approaching 100 terabytes per second, all with microsecond latency. Building that classical nervous system is arguably as big a challenge as building the quantum processor itself. The ultimate bottleneck might even end up being classical, not quantum.
It's an astonishingly complex system, top to bottom, and this immense effort isn't just happening in university labs, is it? It feels like a global race with huge stakes.
It absolutely is. Quantum technology is seen as strategically vital by governments worldwide. It's about economic competitiveness, national security, scientific leadership, the whole package. We're seeing massive national quantum initiatives. The United States passed the National Quantum Initiative Act back in 2018, coordinating efforts across numerous federal agencies like the Department of Energy, NSF, NIST. There's a big focus on fundamental science, building a quantum workforce, fostering industry through consortia like the QEDC, and crucially, managing the transition to post-quantum cryptography.
Right, we'll come back to that PQC point. What about other major players?
China has declared quantum a top national priority, pouring enormous resources into its estimates often exceed $15 billion. They've achieved notable successes, like the MESISA satellite for quantum communication, and established major national labs. Their stated goal is clearly to leapfrog and surpass the U.S. in key areas. The European Union launched its $1 billion quantum flagship program, and that's on top of significant national investments, especially from countries like Germany, bringing the total European public investment well over $10 billion. And you see strong programs and significant funding in the UK, over $4 billion pledged. Canada, a pioneer in quantum research funding, Australia, Japan, the Netherlands. It's truly a global endeavor, marked by both intense competition and necessary collaboration.
So huge government investment. How does that compare to private money flowing into the field?
That's an interesting dynamic. Globally, public funding still significantly outweighs cumulative private venture investment. We're talking maybe over $40 billion in public funds announced or spent, versus maybe around $15 billion in total private funding up to early 2024 or so. That reflects the fact that a lot of this is still long-term, high-risk, fundamental research and development. It takes patient capital.
But is private investment growing?
Oh, dramatically. After a bit of a slowdown, it surged again. Reports showed maybe $2 billion in 2024 and then a huge jump in the first quarter of 2025, maybe over $1.25 billion just in Q1, more than doubled the previous year's Q1. Quantum computing hardware companies tend to attract the lion's share of that funding.
Is the investment spread evenly geographically?
Not really. There's a noticeable split. While China leads in announced public spending, the U.S. dominates private venture capital investment in quantum startups, capturing something like 44% of the global total. It highlights different models. China, and to some extent the EU, have a more state-directed approach, while the U.S. ecosystem is heavily driven by venture-backed startups spun out of universities alongside the big tech companies.
And what are the market projections looking like? Is this becoming a real industry?
It's starting to. Projections for the quantum computing market alone were around $700 million in 2024, expected to cross $1 billion in 2025. Looking further out, estimates for the total quantum market, including computing, communications, and sensing, vary wildly, but some put it potentially reaching nearly $100 billion by 2035, maybe $200 billion by 2040. Still speculative, but indicates the perceived potential.
Okay, so who are the main companies and institutions we should be watching in this space?
It's a mix. You have the established tech giants making major plays, IBM with its superconducting systems, Qiskit software platform, and cloud access. Google Quantum AI, also strong in superconducting qubits, famous for its early quantum supremacy claims. Quantinuum, formed from Honeywell Quantum Solutions and Cambridge Quantum, is a leader in trapped ion hardware and software. Microsoft is pursuing ambitious topological qubits and offers cloud access via Azure Quantum. And Amazon Web Services, AWS, provides access to various hardware platforms through its Bracket Cloud service.
So the big cloud players are definitely involved.
Absolutely, providing access is key. Then you have a vibrant ecosystem of specialized hardware startups, often focusing on a specific qubit modality. IonQ, trapped ions, Rigetti computing, superconducting, D-wave systems, quantum annealing, a different approach, sequential photonics, Quera computing, neutral atoms, and many others. And underpinning all this are the world-leading academic and government research hubs, places like MIT, University of Chicago, Stanford, Berkeley, University of Maryland, Yale in the U.S., national labs like Argonne, Fermilab, Oak Ridge, NIST, the University of Waterloo in Canada, Oxford and Cambridge in the UK, ETH Zurich in Switzerland, Tsinghua and USTC in China, QuadTech in the Netherlands. These are crucial sources of talent and breakthroughs.
It seems like many players are trying to offer the whole package: hardware, software, cloud access.
Yes, there's a strong trend towards becoming full-stack providers. It's not just about building the best qubit. It's about providing the tools, like software development kits, SDKs, and the cloud platforms to make the hardware accessible. This helps build the developer community and ecosystem needed to actually find useful near-term applications for these NISQ devices, even before we get to full fault tolerance. It's about lowering the barrier to entry.
Okay, this has been a fantastic overview of the technology in the global landscape. Let's pivot now to the impacts. What does this all mean for you, the listener, and for society? This revolution seems poised to bring about profound changes, but maybe also raises some serious questions.
Definitely. The potential disruptions cut across many sectors. In national security and defense, as we touched on, think about unjammable navigation using quantum sensors when GPS is down, much more sensitive radar or magnetic anomaly detectors, and potentially perfectly secure communication links using QKD.
But that security aspect cuts both ways, doesn't it? This brings us back to the Q-Day threat you mentioned. Can you explain that a bit more? It sounds critical.
It is critical. Q-Day is the hypothetical future day, when a sufficiently powerful, fault-tolerant quantum computer exists that can break the encryption algorithms currently protecting most of the world's sensitive data, things like RSA and ECC encryption. The immediate threat isn't just about that future day, though. It's a harvest now, decrypt later, or HNDL scenario. Adversaries, state-sponsored or criminal, are almost certainly capturing and storing large amounts of encrypted data right now, data that might seem secure today.
But won't be once Q-Day arrives. They're just waiting.
Exactly. They're hoarding potentially valuable government secrets, corporate intellectual property, financial data, personal communications, anything encrypted with current methods waiting for the day they have a quantum computer capable of decrypting it all. This is why the transition to post-quantum cryptography, PQC, is so incredibly urgent. We need to switch our security infrastructure to new algorithms believed to be resistant to both classical and quantum computers before Q-Day arrives.
So this isn't a future problem, it's a today problem because of data being harvested now. Okay. What about other sectors? Finance.
Finance is another area with huge potential. Quantum algorithms could revolutionize complex optimization problems in portfolio management or trade execution. They could drastically speed up Monte Carlo simulations used for risk analysis. And quantum machine learning might offer new ways to detect sophisticated financial fraud.
Healthcare sounds like another big one.
Immense potential there. In healthcare and pharmaceuticals, the ability to accurately simulate molecular interactions, as we discussed with quantum simulation, could dramatically accelerate the discovery and design of new drugs and therapies. It could shorten R&D cycles that currently take years and cost billions. And analyzing complex biological data, like genomics for personalized medicine, could also be transformed.
And materials science.
Yes, material science and chemistry. Beyond drugs, designing entirely new materials with tailored properties, think efficient catalysts for industrial processes to reduce energy consumption and pollution, better materials for batteries, maybe even finally cracking the puzzle of room temperature superconductors. The economic and environmental implications are just massive.
The potential upside is staggering. But what about the societal and ethical side? Beyond the urgent need for PQC, what else should we be thinking about?
Well, the PQC migration itself is a monumental task. NIST, the U.S. standards body, has standardized the first set of PQC algorithms, but deploying them across the entire global digital infrastructure software, hardware, internet protocols is a massive, complex, and absolutely critical undertaking that will take years. Then there's the issue of economic disruption and the workforce. Quantum technologies will undoubtedly create enormous economic value and new high-skilled jobs, but there's also a risk of exacerbating existing digital divides if we don't proactively invest in widespread STEM education, retraining programs, and ensuring equitable access to these future opportunities. We need a quantum-ready workforce.
That makes sense. What about misuse?
That's a serious concern, especially with dual-use technologies. The same quantum sensor that helps geologists find water could potentially be used by a military to track submarines with greater stealth. Developing norms for responsible development, international governance frameworks, securing supply chains, and trying to prevent a destabilizing quantum arms race are all critical challenges that need global attention.
The intersection with AI.
Yes, the combination of quantum computing and artificial intelligence is another area freighted with ethical questions. Quantum algorithms might significantly accelerate certain AI tasks, potentially leading to breakthroughs, but also enabling unprecedented capabilities in data analysis. This raises profound concerns about mass surveillance, the potential erosion of privacy, and even new forms of manipulation if not carefully managed.
So a lot to grapple with on the societal front. Bringing this all together then, if we look at the path forward, it seems like this multi-decade journey is really defined by overcoming that quantum fragility, primarily through error correction.
I think that's right. And what's becoming clear is that the end state, the quantum future, probably isn't going to be one giant monolithic quantum computer in a basement somewhere, replacing all classical machines. That's not the most likely picture. Instead, think about a hybrid and distributed future. Imagine a global network connecting many different types of specialized quantum devices. You'd have incredibly precise quantum sensors feeding data, dedicated quantum simulators tackling specific materials or chemistry problems, maybe small to medium scale quantum processors acting as accelerators for certain tasks.
All working together.
Exactly. All interconnected by secure quantum communication links and working closely in tandem with the most powerful classical supercomputers. In this vision, quantum devices act more like powerful coprocessors or specialized nodes within a larger heterogeneous computing infrastructure. They tackle the specific problems where quantum mechanics offers a unique exponential advantage. So this revolution might be less about building a single quantum mainframe and more about creating a globally interconnected, quantum accelerated, and quantum secured information ecosystem.
That's a really compelling vision of a hybrid future. What an incredible journey we've taken today. We went from understanding this fundamental shift towards control at the quantum level through the four main pillars of the technology: computing, communication, sensing, simulation, looked at the amazing engineering breakthroughs making it possible, faced the huge challenge of quantum fragility and error correction, and surveyed the global race to actually build this future.
And it's striking, isn't it? The shadow cast by these future quantum capabilities is already forcing massive real-world action today. Just look at the urgency around the global PQC migration. It really illustrates the profound, almost preemptive impact this revolution is already having, even before the most powerful technology is fully mature.
Absolutely. So, for you, the listener, perhaps the key takeaway is that this quantum future isn't some far-off science fiction dream. It's actively being built, engineered, integrated, and debated right now, with all its incredible potential and complexities. It really leaves you wondering, how do you see these technologies eventually impacting your world? And what new questions does this deep dive raise for you? Thank you for joining us on this deep dive today.